We're on to chapter 5 already. So here we'll be talking about graphs and Euler circuits. Everyone always gets the name pronounced wrong here. This is not Euler, it's Euler. That's just common thing people mess up. Euler. Okay. Airports. Suppose that we wanted to represent airports with a picture that shows when two airports have a connecting flight. So okay, here we have all of the information is just recorded in a table, right? So the table is saying, New York, there's a flight from New York to Atlanta. There's an X in the table. And the table is symmetric too. So there's also, because there's a flight from New York to Atlanta, there's also going to be a flight from Atlanta to New York, right? So it's symmetric like that. All right, so this table, it's a pretty small table of data, right? But it's like it only has 4 airports, but it's still kind of hard to sort of parse this. Like if you wanted to like kind of think like, all right, I want to get from like Hartford to New York, like what's like the most efficient way to do that? Like you would think, all right, well I go to Hartford, and then I have to go to Atlanta. So okay, where can I get from Atlanta? I'll go to Atlanta. Okay, from Atlanta I can get to New York. But if there wasn't a route to New York, then you would have to like go to LAX and then check like, okay, is there a route from LAX to New York? And so like if this table were like any bigger, it would just like rapidly get like harder and harder to sort of deal with. So one way that you could sort of represent this with a picture is as follows. So each of the airports will get like a little dot. So we'll get like a little dot for New York, get like a little dot for Hartford. I'll just say BDL because that's what we call Hartford Airport. LAX, Los Angeles Airport, and and then what's the last one? Atlanta, ATL. Okay, and then I'm going to put a line connecting the two airports if there is a flight connecting them. So New York has flights to Atlanta and LAX. So New York to LAX, and then New York to Atlanta. Those are going to be things. Whatever, good enough. Okay, and then Atlanta, let's do Hartford next. Hartford has a flight to Atlanta, and that's it. Okay, and then we had a flight from Atlanta to New York and Hartford. Okay, those are both already taken care of. Oh, and also LAX. So draw that one in. And then LAX has one to New York, has one to Atlanta, and does not have one to Hartford. So it looks like we've kind of labeled everything that we sort of need to here. So this is an example of a graph. And the 4 dots, we call these vertices of the graph. And the lines, we call these edges of the graph. So this graph is like really useful in this situation because now like visually you can just see like, all right, if I want to get from Hartford to New York, I just have to go Hartford, Atlanta, New York. This is visually a lot cleaner to just kind of see like you're just going to sort of draw out like a path from this vertex to that vertex ending at that vertex. Okay, so like I said, that's an example of a graph. A graph is by definition just a set of points and lines. Points are called vertices. The lines are called edges. The edges connect the vertices. So you could have like all different kinds of graphs. So you could have something like this. The lines are allowed to cross over each other like this. That doesn't like create an extra vertex or something like that. Like this graph is like inherently like the same as like this. Wait. like I could take this middle line right here and I could just draw it like this. And like if these represent like those 4 airports or something like that, like, you know, all we care about is that there's a flight going from this airport to that airport. We don't really care like what the line really looks like. We just care that there's like just some connection between the two, right? Okay. Yeah, some more basic examples. Graphs could look connected or they could be disconnected. So this is an example of a connected graph, meaning that basically you can get from any vertex and then travel along the graph to get to any other vertex. That is not the case for like this graph over here. If I start right here, I can never like draw like a path that ends up over here. Same thing for this one right here. Even though this one kind of looks a little bit connected because like this line is like crossing over this other line, this would mean that, you know, in terms of like the flights, there's a connection from this airport to this airport, and there's a connection from this airport to this airport. But there's no, like, just because like the line is drawn like this doesn't mean that like there's some middle airport in between the two. Like that doesn't really make sense. So like this graph is basically the same as like this graph, right? There's no difference between those graphs fundamentally. They're the same. Graphs could have multiple edges. So this doesn't really make as much sense in like the flight example, but like it will make sense in context that we'll see definitely later on in this video, for sure. And just there are like many examples where like having multiple edges between vertices just kind of makes a lot of sense to do that. So we'll allow for that sometimes. A lot of times people will not allow for multiple edges between vertices, and there will be like good reason for doing that. Like for example, in the airports example, it doesn't make sense to have those there, but it happens sometimes. Same with loops. So a loop is basically just it's an edge starting and ending at the same vertex. So this is a loop right here, and this is a loop right here. Again, this doesn't always make sense in the real world context, but it does in a lot of them. So in the airports example, like it doesn't make sense for there to be a connecting flight from one airport to itself. But there are other like contexts out there where it does make sense to have a loop. Trying to think of like one off the top of my head. Yeah, I can't think of one off the top of my head. Maybe I'll like think of it later and put it in the comments or something like that. But yeah, this does make sense in a lot of contexts, and so sometimes it'll pop up. Anyway, empty and complete graphs. A complete graph, so these are complete graphs over here. These are empty graphs. It's empty because it doesn't have any edges in it. So there are just vertices. There aren't any edges connecting the vertices. So in terms of like connected and disconnected, the empty graphs are like extremely disconnected graphs, right? Unless there's like only one vertex. As long as there are multiple vertices and no edges, it's going to be disconnected, right? It's empty. Complete graphs just means that like there are like you've used all of the possible edges. So like there is an edge from every vertex to every other vertex. So this vertex here has an edge to all of the other 3 vertices. This vertex here has an edge to all of the 3 other vertices. Same over here. This is a complete graph with 5 vertices. This one is connected to all of the other 4. Same for every other vertex in this graph. If I were to remove any one of the edges in this graph, it is no longer complete. It's missing one. Oh, by the way, I've been saying this out loud. Plural of vertex is vertices. So vertices is plural. Vertex is singular. Okay, so our airline graph from example 1 looked kind of like this. So ironically, I did not plan this. I like rehearsed the video like before doing this, and when I did it, I drew it the way that I drew it over there, and then I copy and paste it. But the whole point of this, so we actually drew it like this. But what if we drew it like this? Is this stuff like recording the same information, right? So the upshot is yes, these two graphs are recording the same information. So BDL is only connected to Atlanta. Oh wait, did I screw up? Yeah. Okay. Hartford is only connected to Atlanta. Yeah. Okay. Whatever. This is okay. Anyway, I don't want to restart, so I'm just gonna kind of roll with this. Okay. So this is what our graph looked like, but we could just like draw this graph differently. So the other graph was like different because that one said, what did it say? It said that there was a flight from LAX to BDL. So these two graphs are inherently different because they're recording different information. But if there's a flight from Hartford to Atlanta, and if I were to just like draw it differently, like if I were to just take this and draw this like that, something like that, I am still recording the same information. I could even like kind of put LAX over here. This is still like recording the same information of, hey, there's a flight from this guy to this guy. There's a flight from this guy to this guy, here to here, and here to here. Even though it's like recording the same information, even though it like looks different, it's still recording the same information. And so we would consider these graphs to be the same. They don't look identical, but we would consider them to be equivalent. The one that I like mistakenly drew earlier in my like test run before recording this, that one was not equivalent because it was recording different information. So that's actually, just inherently different. So looking at the labeling very much matters. So, and so if I were to like change like these two labels right here, so change Atlanta and BDL, Hartford. Now this is a inherently different graph. If I change the labeling, this is recording different information. So before there was a flight from Atlanta to New York, but now there is no flight from Atlanta to New York. There's no edge there. So you have to so even if they look the same, try to do this guy and then just literally duplicate it, but then just swap the labels, then all of a sudden this is just different. So labeling matters even if they look the same. So I recommend pausing the video and seeing if you can determine whether the following two graphs are equivalent, and then unpause and then see. So there's like two parts here. This is like your part A, this is your part B. So are these two graphs equivalent, and then are these two graphs equivalent? Okay. So pause, give you a couple seconds, catch your breath, and then come back, see if you get the same answer. It's me. All right, so with this first one, it's kind of hard to see, but like, let's see if it's like recording all the same information. So A is connected to B and C. Is that true over here? Yeah, A is connected to B and C. B is connected to A, D, and E. B is connected to A, D, and E over here as well. Good. D is connected to B and C. D is connected to B and C. C is connected to D, A, and E. C is connected to D, A, and E. And then E is connected to B and C. Connected to B and C. I think I've done it for all the vertices now. So it looks like they're recording the same information. So that leads me to believe, yes, they are the same because they're recording the same information. I could also just kind of mess around with the picture a little bit to make them look identical. So here I'm just kind of moving stuff around, and then let's move the vertex E all the way over here. Oops. Just want to do this. So grab that and move that over here, and now, bam, we get something that looks just completely identical. Over here, though, these are not recording the same information. Let's see. For example, let's see. A is connected to B and C, but over here, A is connected to B and E, so not C. So yeah, because these two graphs are recording different information, then they would not be considered equivalent. Another way that you could do this is by looking at like sort of properties of the graphs and properties of the vertices. So one property that you could kind of look at is, well, how many things is C connected to over here? Well, C is connected to 3 other vertices, and over here, C is connected to 2 other vertices. We would call the number of things that C is connected to the degree of that vertex. So the degree of C in this vertex is 3, and the degree of C in this vertex is 2. And so if the two graphs were equivalent, then the degree of like all the corresponding vertices should be the same in each of the two graphs, like it is up here. A is connected to B and C over here, A is connected to B and C over here. Therefore, the degree of A has to be 2 in both of those two equivalent graphs. That's not the case down here because the degrees are different. They're recording different information. So yeah, this is the definition. The degree of a vertex is the number of vertices it is connected to by an edge. Okay, Königsberg bridge problem. So this is a slight departure from previous stuff. Suppose that we wanted to walk across every bridge in this little land before returning back to our starting point. Let's say like the bridges are like really pretty bridges, and you just like wanted to kind of like stroll through the town and check out all of the bridges. And let's say that you don't like you want to be efficient, like you want to like kind of get home soon, so you don't want to do any backtracking if you don't have to. So can we like minimize like the backtracking here? So is this possible? So we can give it a go. So let's say that we wanted to start up here. So the starting point is in these types of problems is typically not going to matter. It will for like something we'll do like at the very end of today's section, but not for this. So let's say we start at the top right here. Let's say we want to cross this bridge right here. Now I'm over here. So let's say we cross this bridge. Now, we only have 2 options. Let's go over here. We end up back here at this land, and then we cross this bridge, I guess. And then this is where we kind of get a little stuck. So we could maybe go down this way, but if we go down this way, we don't have any bridges that we can cross anymore. Like we're just like stranded over here. And then we would be like forced to backtrack. If we didn't do that, so let's say that like we went back up here. Okay, so now we're like back to our starting place. There's still 2 more bridges that we have to cross. So we have to cross this bridge. But now we've like neglected this bridge and we're like still not back where we started, right? So it seems like there are like some issues here. Okay. This is a very famous problem in graph theory, like any graph theory like class that like someone will ever take, like this Königsberg bridge problem. This is like an actual problem that like showed up and like prompted a lot of studies. It's basically all about something called Euler circuits. So as I mentioned earlier, pronunciation is Euler. An Euler circuit is a circuit that uses each edge in the graph exactly once. The graph is Eulerian if it has an Euler circuit. What do I mean by circuit? I just mean it is like a loop in the graph. Like it's a sequence of just like walking along the edges and then getting back to where you started. So if I were to like draw a graph over here, One circuit that you could draw over here would be, sorry, I should use like a smaller highlighter. You could do this circuit right here. This would be like one circuit where you start up at this top one, go down here, go over here, go over here. This is not an Euler circuit because it doesn't use all of the edges in the graph though. Okay. This graph right here does not happen to have an Euler circuit. If I were to draw a slightly different graph, let's maybe draw, let's say something like this. Something like this. Yeah, something like this. This will have an Euler circuit. Let's say that I want to start right here. Go up, and then I could go down, over, up, to the right, and then back left again. So this would be a circuit because I'm traveling along the graph, and then I'm ending back where I started, and it's an Euler circuit because it uses every one of the graphs. And I'm not using any of the graphs I'm using every one of the edges exactly once. I'm not like doubling up. I'm not doing any backtracking, anything like that. Okay. So it turns out that there is no Euler circuit for this Königsberg bridge problem. So what we can do actually is we could translate this bridge problem into a graph theory problem. How can we do that? Well, my picture earlier kind of hinted at it. So we can create a vertex, a graph where we have one vertex for each piece of land, and then we will have an edge connecting two vertices for every bridge that is connecting two pieces of land. So we'll have one edge right there. We'll have another edge right there. Have an edge over here. We'll have an edge over here. Edge over here. Edge over here. And edge over here. So this is a graph. I can just duplicate this over here. So this is a graph. Notice that we have a bunch of multi-edges in the graph. These two vertices are connected by multiple edges, right? We said that was fine in some situations earlier. And then, so we're basically asking, is there an Euler circuit in this graph? And the answer is, for this graph, no, there is not. You can if you start no matter where you start, you could kind of try this. You'll eventually just kind of get stuck. Okay, but what if we don't care about returning to our starting point? Is there a chance that we can do it if we don't require that we have to get back to wherever we started? So if I were to take this let's take that and over here, get rid of that. That. Okay, so let's say that I want to start up here and then maybe just travel along it, and I don't necessarily have to make it a circuit. I don't necessarily have to get back to where I started. So is that a possibility? So you can try and then just go this way, maybe go this way. Okay, well, you see maybe this is a problem because now if I go down, then I have to backtrack. So seems problematic already. So maybe I shouldn't have done that. So let's go this way. And then, oh, hey, this is also problematic. So maybe I should have done something different over here. So let's go this way, maybe go that way, that way. And now there are two options. I could go either this way or I could go this way, but I can't do both. So it seems like the answer for this one is no as well. We're not really justifying it here, but it seems likely that the answer is no. Yeah, okay. So anyway, this would be called an if the answer were yes to this, then that would mean that we found not an Euler circuit, but an Euler path. A path is just similar to a circuit. You just kind of travel along edges in the graph, but you don't necessarily have to end up where you started. So for example, a circuit is also a path, but it's a closed path. Closed path just means that like the first and end vertices are the same. Okay, so the Eulerian graph theorem is a very handy theorem that kind of just like gives you an easy thing to check to determine whether or not a graph has an Euler circuit. So a graph has an Euler circuit, it's Eulerian, if and only if the degree of the vertex is even. Okay, so yeah, okay, so in this right here, I can, maybe I should just bring this back to the other page actually. Okay, so here is our Königsberg bridge graph. I'm going to list the degree of each vertex. So this degree right here is 3, because there are 3 edges coming out of it. This degree is 5, this degree is 3, this degree is 3. And so, because like, not only is it false that like that all of the vertices have even degree, like not a single one of the vertices have an even degree. So this is like very, very far from being Eulerian, right? Understanding like why this is true is actually also not too bad. So let's say that like we have an odd vertex in the graph. Let's just say like for simplicity's sake that there are 3. If you needed to have a circuit that like has no backtracking and uses all of the edges in the graph, at some point you would have to travel along like one of these edges, might as well be this one. And then from here, if you go, like you have 2 options, so you could go this way or you could go the other way. And if you go this way, then eventually you will have to you can't backtrack and then use this edge. Like eventually you'd have to like kind of come back to this via some other route and then you would use that vertex. But then if you did that, then you would be stuck at this vertex. So this vertex right here would have to be the place that you started at, but it can't be the place that you started at because like you got to this vertex from somewhere else, like you came at it from this way. So it's just impossible for this to work as long as you have a single odd vertex. This argument works just as well if you have like 5, because then, you know, if you have 5, then like, okay, you come in here, you go out here, and then eventually like you come in and then you come out again, and then same sort of problem happens. Okay, so are the following graphs Eulerian? Is there an Euler circuit? So you could just kind of test this and just, you know, use some inductive reasoning to get a feel for whether or not there's an Euler circuit. Or you could just count the degree of each vertex. So this vertex has 2 edges coming out of it. This vertex has 1, 2, 3, 4. This says 2, this says 2, this says 2, this says 4. And so by this theorem, all of the vertices have an even degree. Therefore, it is Eulerian. So this one's a yes. This one right here, this edge right here has, this vertex here has 3 edges coming out of it. So automatically, I don't even have to count the other ones because it's not true that every vertex is even. As long as there's one that's not even, then it can't have an Euler circuit. Okay, what about this one over here? This vertex has degree 2. This has 4. This has 2. This has 3, and then this has 3. So this one would also not be Euler or Eulerian because these 2 vertices have odd degree. So this one would also be a no. Okay. Here's like another sort of application of this. So Christmas lights. Let's say that like we want to like drive down all the streets and we want to like look at the Christmas lights on like all of the streets. So let's say we have like a graph representing a neighborhood where each represents a street, and maybe we like don't like include the edge in the graph if like that street doesn't have any Christmas lights or something like that. And then each of the vertices is just going to be like a corner here. So let's say that Tanya wants to drive down every street exactly once to see all the Christmas lights before ending back at home. So is this possible? So we can now use our Eulerian graph theorem to talk about this. So we can just kind of say like, let's count the degrees of the vertices. So this vertex up here has degree 2. This is 2. This is 4, 4, 3. Okay, so this one over here is 3. So automatically we can say that no, there's no Euler circuit. So there's no way to travel along everywhere here, all of the edges, and then get back to where you started without doing any backtracking. All right, well, what about this one over here? Well, this one would also be a no, because like you can just kind of see like, well, what about the home? The home just has degree 3 right there. And even if like all the other ones are even, then it's just not going to work out. Okay, but what if Tanya doesn't care about necessarily ending back at home? Okay, so let's say that like she wants we're looking for an Euler path, just a path that uses all of the edges in the graph, but doesn't necessarily end up where you started from. Okay, so our theorem before was only for circuits, so not necessarily for Euler paths. So what we can do is actually use the following theorem, which is the Euler path theorem. This is a very similar theorem. It says that a graph has an Euler path if and only if there are only 2 or less vertices with even degree. Technically, this could say 2 or 0 vertices with even degree. If there are 0 vertices with even degree, then that falls under the like previous theorem where it has an Euler circuit, in which case you would actually end up where you started, necessarily actually. But if you want, if there are 2 vertices, it's impossible for there to be exactly one odd vertex. But if there are 2, then those 2 vertices will end up being your starting and ending points. So back to this, counting even and odd degrees. So this is even, this is odd, this is odd, even, this is odd, this is odd, this is even. I could keep going, but all of a sudden, immediately we have more than 2 vertices with odd degree. Oh shoot, this was supposed to say odd degree. I'm at the end of the video, so I don't want to re-record the whole thing because I had like a typo at the last slide, but please bear with me. Okay, yeah, so there has to be 2 or 0 vertices with odd degree. If there are no vertices with odd degree, that means that everything is even, and then there must be an Euler circuit according to the previous theorem. If there are 2, then there will be an Euler path. So this one right here has more than 2 odd vertices, and so this again would be a no. But what about in this one over here? So this one, let's count the degrees. 2, 2. This will be 4, 2. That one would be 4, 2, 2, 4, 4. This one is 5. This is 2. This is 4. And this one is 3. So this one does have exactly 2 vertices with odd degree. This one and this one. And so that tells us that, yes, there is going to be an Euler path. So let's see if we can actually find one. So let's start at home, and it does matter that we're starting at one of the odd vertices. If like home was like over here, then we wouldn't actually be able to do this unless we started at the odd vertex. Okay, so we'll start at home. Let's go this way, this way, this way. A lot of the choices that you make here are not really going to matter. You just kind of like make choices until you're sort of forced into doing something. Let's go this way, this way, this way. So if we haven't like repeated anything, we haven't. Okay, now we're forced to go down this way. We're forced to go up this way, and then we're forced to go to the left here. And so we end up at this other odd vertex right here. And so we haven't done any backtracking. We haven't we haven't done any backtracking, and we've used all of the edges in the graph exactly once. And so we have found an Euler path.